In this paper, we explore the question, what could a computer learn about objects simply by watching lots of YouTube? In other words, given videos like these, we seek to automatically extract high-precision, pixel-level spatiotemporal masks for the relevant objects in each video. The key challenge is to take these noisy, video-level annotations and to generate masks that separate the object from the background without ever having seen such masks during training. Let's consider a detailed example. Say that we want to learn object masks for the concept dog. Our training set will be several thousand videos that are likely to contain dogs, such as the one shown here. Note that we don't actually know which pixels belong to the dog and which belong to the background. Our negative set contains large numbers of videos that probably don't contain dogs. Our hope is that we can learn what differentiates dog pixels from the background by watching many such videos. We represent each video using a collection of spatiotemporal segments. These segments are simply regions of pixels similar to superpixels that are connected across both space and time. One of the key reasons to use space-time segmentation in video rather than traditional segmentation on individual frames is that we can exploit motion to better separate pixels corresponding to objects from those corresponding to background. We represent each segment using bags of features such as color, shape, and texture aggregated over the entire segment. Each video in the positive and negative sets has now been converted into many thousands of segments. Our goal is to learn a segment-level classifier even though our label information is at the video level. This problem bears some similarity to noisy multiple instance learning, with segments corresponding to instances and videos corresponding to bags. The major difference is that our primary goal is instance level rather than bag level classification. We consider several strategies for tackling this weakly supervised learning problem. The two key issues are that they must contend with noisy training data, since our video level labels are not perfect, and that they must scale to millions of segments taken from tens of thousands of training videos. Details about these algorithms can be found in the paper. Here we show the segment-level inference pipeline in action. We see that the spatiotemporal segmentation does a decent job at separating object pixels from the background, even though the dog is splashing in water. And we see that the segment-level inference correctly classifies several segments on the puppy as belonging to the dog class. These are results on the robot class. Note that due to under-segmentation, the black line in the background is grouped with the object. However, we still extract the robot. Next stage takes the segment-level classifications as seeds and refines a pixel-level mask for the object using graph cuts, as detailed in the paper. Decoupling the segment-level inference from the mask refinement allows us to easily scale up to very large videos. We now show additional examples of our method on a variety of object categories. In the paper, we also provide quantitative precision recall results obtained using a dataset of 20,000 videos from which we manually annotated a ground truth set of 50,000 frames with pixel-level object masks for each category. We are the first to tackle the idea of learning object masks from internet video under weak supervision, and we hope that our work encourages other researchers to also explore this problem. We show some hard cases where our method fails. Since our algorithms have no access to supervised training data, object classes that consistently co-occur with distinctive backgrounds continue to pose a challenge. For example, water is relatively rare in our dataset, yet it is frequently associated with boats. Similarly, riding gear in show jumping arenas are observed only with horses. The helicopter class is difficult because the object typically occupies only a small area in the frame, and its rotors cause our current spatiotemporal segmentation method to fail.